Welcome to our video on logarithmic growth. Here are our objectives. Again, we want to just understand what this type of growth is and be able to model it, model real world data with these functions. So the functions we're going to study in this video are called logarithms. And logarithms really just allow us to convert numbers so that we can compare large and small numbers alike. That's really all it's about. And on an even more basic level, a logarithm is really just the inverse of an exponential function. So if we have a regular exponential function b to the x and we say we're going to let that equal some number a, then the logarithm with base b of a is x. It undoes it. So log base b of a equals x means b to the x equals a. And one of the ways I always remembered it as a student was with the spiral, right? B to the x equals a. Kind of goes around in a spiral. And that reminds me that logs are really just exponential functions in reverse. They're kind of like Jeopardy, where they ask a question by giving you the answer, and then you have to answer it in the form of a question. That's all it is. Because if they say, let's say log base 3 of 27 equals x. What this is really asking is 3 to what power equals 27? And you go, oh, well, 3 cubed equals 27. The answer is 3, right? Or if they say log base 2 of 256 equals y, or whatever you want to call that letter. And that's really saying 2 to what power equals 256, right? So you see how you're solving for a power rather than just saying 2 to the, what is it, the 10, 9, 8, I think 2 to the 8th is 256? Yeah, 2 to the 8th. So instead of just saying 2 to the 8th equals 256, which is pretty straight, it's kind of like they just say 2 to the 8th equals what? And you just plug that in my calculator. That's a straightforward question. That's really easy. But that's not what they're doing. They're asking the question in reverse. They're saying, okay, I'm going to give you the answer. I'm going to give you 256 and tell you it's going to be a power of 2. And now you got to solve backwards and figure out what power of 2 is 256. And that's all a log is, right? It takes log base 2 of 256, and it spits out the answer 8. And you might say, well, that's really easy. Well, yeah, it's easy for these types of questions, but what happens when you have something like log base 3 of 10 equals? Well, now that's saying 3 to what power equals 10. You're like, oh, crap, I can't do that one because 3 squared is 9, 3 cubed is 27. All I know is it's somewhere between 2 and 3. It's going to be 2 point something. All right, well, now we've got to figure out a way to do these, to calculate these. And unfortunately, we can't do them by hand. It's a calculator thing. And most calculators couldn't do base 3, so we would have to use change of base and put it into a different base and put it in the calculator. But that's a discussion for later. Just want you guys to realize that log questions are really just exponential questions in disguise, which is why we have these same rules that we had for exponentials. Remember in exponentials, b has to be greater than 0, can't be equal to 1. Well, the same thing here, right? The base, because that's the same b, has to be greater than 0, can't equal 1. And in this case, a also has to be greater than 0. But that makes sense because if you take a positive number, right, something that's greater than 0, and raise it to a power, any power you choose, the answer will also always be positive. Right? So it's not like we're just making that up. It just comes from this relationship, right? This relationship forces all of this to happen. All right, skill check. Give this one a try. Right? This means 5 squared equals 25. Good, easy, right? All right, let's see some other examples. Can we write each of these as exponentials? Well, 4 squared equals x, right? B to the 4th equals 81, and 5 to the x equals 125. Simple and easy. All right, how about going the other way, right? If 8 to the x equals x, how do you write that, right? Well, it means log base 8 of x equals something. In this case, 3. Now you might be asking yourself, well, where the heck did that 3 come from? Well, the 3 came from a typo, right? This should have been a 3. That should have been 8 cubed equals x. And then that's where you would have got that. All right. The next one, log base x, of 16 equals 4. Because remember, we're basically kind of undoing this question, right? X to the 4th equals 16. 6 to the x equals 216, which means 6 is my base, right? Because this is my base. The power is always the thing over here, and then 216, the answer, right? So the answer goes there. The power, right? The exponent goes here, and then the base is here. That's how you can convert. Because it's easy to go from logs to exponents because you got the nice little circular trick I showed you guys. But going in the opposite direction takes a little kind of memorization. That power's on the right, the answer is, in the log, so to speak, and then the base is the base. Okay, the common log is just a name we give to logs of base 10, and the reason why we do that is because log base 10 shows up in a lot of common things. The decibel readings, seismographs for earthquakes, light intensities, all sorts of things in the natural world show up with base 10, which might make you think, well, then how come that's not called the natural log? Well, because there are other things that are considered, I guess, more natural, and they got the name natural log. So the common log is base 10, and because it happens so much, we just take the 10 away. And so anytime you see log of x and there's no base down here, it's assumed to be base 10. It's the same argument as to why we just say this is the square root of 2, whereas this is the cube root of 2, right? If we're going to do any root other than the square root, we put a number in there. So we could do the 4th root of 2, right? Or the 10th root of 2. But if we're going to do the square root, we're just going to put nothing in there. Because there's no point in labeling all of them. We can take one of the labels away. Just one, can't take two. You take one label away, and then you still know what everything is. Because if it's the one thing that's not labeled, then it's the one thing we don't label, right? So we did the same thing with logs. We're like, all right, we're lazy. We don't want to have to label all the logs. So let's take one of them that we use the most, and let that be the one that we're not going to label. And we're going to call that just log x. And later on, we found out, oh crap, there's this whole other group of logs that we use a lot as well, natural logs, and we don't want to have to keep labeling them, so we gave it another name as well, so we didn't have to keep labeling that one, and we'll talk about that one a little later. All right, so here's another example. Past research tells us that our bodies grow at a given rate based on our DNA and the environmental factors in which we grow up. Assume that a baby girl is born and is 22 inches long. If we consider that the baby will grow at a rate proportional to her body size until adulthood, then the percentage of her adult height attained can be modeled by the logarithmic function this. Now, it's pretty thankful that we grow at a logarithmic rate and not an exponential rate, because if we grew at an exponential rate, we'd all be like 3,000 feet tall. Logarithms grow really, really slow, right? They grow fast in the beginning and then they slow down to where their growth is almost imperceptible. Whereas exponential functions grow really slow in the beginning and then they shoot up and grow really fast in the end. Can you see how those are opposites of each other? Logs and exponents are inverse functions of each other. They do everything kind of in reverse order. Now, X is going to represent her age in years between 0 and 25. And the reason why it's only between 0 and 25 is, well, for one thing, you can't be negative years old. And past 25, the function no longer models growth really well. It only models over that small window is what's happening. One question we could ask is, what percent of the girl's adult height is attained by age 12? Now, if we want to know the percentage of her adult height that she'll get at age 12, then we can evaluate f of 12, plug that into the function, and f of 12 gives us 83.287, or roughly 83% of her adult height is at 12 years of age. Pretty straightforward and easy, right? Okay, how about this skill check? See if you can figure out what percentage of her adult height will be at 18. Well, just plug in 18 and round, and you'll get about 92%. Okay, the Richter scale. That's the thing used to measure the intensity of an earthquake. And as I told you, those tend to be on the log, right, of base 10, and that's why we have no 10 here, right? So this is technically base 10. It's a log with nothing, so it's log base 10. That's the Richter scale. And you just take log of I over I sub 0. And remember, sub 0 always represents the initial thing. So in this formula, R is the magnitude. That's how strong we're going to say an earthquake is. You've heard of, oh, that was a 4.3 or that was a 6.8 on the Richter scale. That's a magnitude of how much energy is displaced. I sub 0 is the intensity of an earthquake that is barely felt. It's what we call a zero-level earthquake. You can think of it as like the initial intensity. And the initial intensity can't be 0 because we can't divide by 0. So that initial starting point has to be something that's a little bit more than 0. It's just barely felt, right? It's almost so mild that you couldn't feel the earth shake. And that's, the lowest intensity earthquake there is. And then everything's based on ratios, right? See, ratios of how intense the new one is to this base idea. Every increase of 1 in the Richter scale means the magnitude of the earthquake is 10 times bigger because we're on this log base 10 scale. All right, so keep that in mind. When you go from a 3.0 to a 4.0, a 4.0 magnitude earthquake is 10 times more intense than a 3.0. So what magnitude would be something that's 1,000 times stronger than a 0 level? Well, we can figure that out by doing the math, and we see that it's 3, which makes sense, right? Because 1,000 is just 10 cubed. So we've gone up by a factor of 10 3 times, and so that would be a 3.0. So a 3.0 earthquake, which is a pretty mild earthquake, is 1,000 times stronger than an earthquake that we can barely feel. Now, there was a very large earthquake back in 2010 that was off the coast of Sumatra, did a lot of damage, and it was a magnitude 7.7. If I sub 0 is thought of as just being 1, which is what it is, then we can figure out the intensity level of a 7.7 earthquake. Because remember, it increases by a power of 10 each time. So this is basically 10 to the 7.7 times stronger, or that much stronger. 50 million times stronger. That's the magnitude. Yikes. Now, there was an earthquake that hit Chile in 1960, and it was estimated to have been about a 9.5. And the reason why we say estimated is because back in 1960, we didn't have a lot of good Richter scales all over the world being able to measure these things precisely, so it had to be basically estimated. And we can now figure out how strong that one is compared to an intensity of 1. So that's 10 to the 9.5, or this huge, huge number, 3.16 billion times stronger than a 0 level earthquake. That number is so big that we can't even wrap our heads around it. I mean, do you really have any idea how big something is if it's 3 billion times stronger, right? Those numbers really don't mean a lot to people. And that's why we have the Richter scale. Because if we told somebody, hey, this earthquake was 3.16 billion times stronger than, people are like, what? I don't even know how big a billion is, right? I mean, I can see the number and I can see all the zeros, but I have no magnitude of that. There's nothing in my life that is 3 billion somethings that I can go, okay, this relates to that, right? I understand 100 times. I understand 1,000 times. I can even really understand 10,000 times. But there's nothing in our world that we deal with that's 3 billion that we can put a scope to this, which is why we have the magnitude scale. We talk about it being a 9.5, and you go, holy crap, 9.5, that's a big number, right? Then I know that's a big, big earthquake. Now, how about if we wanted to figure out how much stronger the Chilean earthquake was than the Sumatran one? So we had one that was 9.5 and another one that was 7.7. So how could we figure that out? How do we get the answer of 60? Well, you'll recall that the Chilean earthquake was a 9.5, which meant its intensity was 10 to the 9.5, and that gave you that big, huge number. And then the Sumatran one was 10 to the 7.7, because that was a 7.7 earthquake. And that gave you its big number. And if we want to know how many times bigger something is than something else, then we can say, 10 to the 9.5 equals 10 to the 7.7 times some x. And if we want to solve for x, we just divide both sides to 10 to the 7.7, right? Because that gives us this ratio, tells us how much bigger it is, how many times bigger it is. Well, hopefully you remember your rules that if I have x to the a over x to the b, that just equals x to the a minus b. So this is going to equal 10 to the 9.5 minus 7.7, which is going to be 10 to the 1.8, which equals 63, roughly, when you round. It's like 63.08 or something like that. Okay, so that's how we can figure that one out. All right, sound intensity, another example of something that's on the scale of 10. So we're using logs, right, because those are base 10. Again, we have this I sub 0, this initial amount thing. And the intensity of the sound I is based on a reference value of I0. And this is the threshold of hearing at 1 kilohertz. So we can consider that to be the softest sound we could hear, right? Remember in the magnitude earthquakes thing, it was the softest or smallest earthquake we could feel. In this one, it's the softest sound we can hear. So if the decibel level of a certain sound is 115 decibels, what is the level of intensity? All we got to do is substitute everything in. Decibels on the left, level of intensity is what we don't know. We know that the initial sound is just 1. So now we're just looking for 115 equals 10 log of I. Divide both sides by 10, and that's where we get 11.5 equals log of I. And if we want to solve for I, we have to basically make both sides of the equation a power of 10. And this is something that we kind of glossed over on the previous examples. But remember, it comes from the idea of this is base 10, right? It's hidden. And it's the base, we wrap it around to this number, equals this thing, right? We normally write it this way. Log base 10 of I equals 11.5. We know that 10 to the 11.5 equals I. So that's how we're getting that 10 to the 11.5 equals I. Plug that into your calculator, and you'll see that it's about that many times greater than silence. Again, 316 billion is a number that we don't really understand. We can't wrap our heads around it. So that's why instead we would just say it has a decibel level of 115. Because then we're talking about things on levels we can understand. I understand what 115 means. And when you tell me something else is 135 decibels, I go, oh, well, that's quite a bit more than 115. So you can put scale to it, just something you can understand. Okay, that natural logarithm I was talking about, that's just a logarithm of base e, where e is an irrational constant. It's like pi, only a different, right? Pi is 3.1459, blah, 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 blah. E is 2.718281828, blah, blah, blah. And it looks like there's a pattern, but there isn't. It goes on and on and on, and it doesn't have a pattern, and it doesn't repeat. It's just like pi. E and natural logs, those types of things are in finance a lot, because exponential growth and then E with logarithms work a lot with money. So E really came out of working with exponential growth and came out of working with money, but it shows up a lot in the natural world as well. So it got the name natural logarithm. And as I said before, that we're lazy, and we didn't want to keep writing log base 10 all the time for those things, so we just made it log. And then we realized, oh crap, we've got this log base E thing that we don't want to write that all the time, so let's give it a whole nother name, and we call it ln for logarithm naturel, which is the French way for natural log. So lnx is your natural log. That's all it means. So it just means a log of base E. Here's one formula that is supposed to model the percentage of information the average person can recall after a certain period of months have passed. So T is time in months. And if you plug it in here, it'll tell you what percentage of that stuff you remember T months later. So if you want to figure out what percentage of this material for this class you'll remember 6 months from now, you plug in a 6 into this formula, which obviously makes a 7 because plus 1, and you just do the math, and you get 55.8. Okay, so this means 6 months from now, and you can hear my dog yelling at whoever rang my doorbell, that the amount of material that was retained was about 56%. All right, hope that helps.